Yeah, okay, welcome back everyone. We're talking about Schwarzschild solution. I had just time enough last Friday to make a few historical remarks, and now we want to start really with the calculations. So what will keep us busy for today is the derivation of the Schwarzschild solution. So this is a solution of what? It's a solution of Einstein's field equation, more precisely of Einstein's vacuum field equation without a cosmological constant. So our goal is to find solution to this equation. Ricci is 0. That's a vacuum field equation without a cosmological constant. And we want to do this, under the assumption of spherical symmetry. So we will have to talk about what it means that a metric is spherically symmetric. And whereas the physical situation we associate with this solution is, of course, that of a spherically symmetric body, which produces a gravitational field in its outside region. And as we are solving only the vacuum equation, we are only concerned with the outside region. We are not concerned with what happens inside the star, only the region outside where we have vacuum. So the goal is that this serves as a model for the space-time around a spherically symmetric star or some other celestial body. So you may think of the sun. It's a good model for the sun. A spherically symmetric star. This will be characterized by two parameters. Namely, it will have a mass, which I will denote capital M. So we will expect the solution to depend on the parameter M in some way or other. And it will have a radius. This will tell us for which region the solution is actually valid. And because I want to assume only spherical symmetry, I will allow that the star pulsates. So the radius may be time dependent. Yeah? So the radius R star may be a function of t. Actually, Schwarzschild derived his solution under the assumption that this is time independent. He considered a static situation from the outset. But what we will find out is that it doesn't matter if we allow for a time dependence of the star. The field outside is precisely the same, independent of how the star pulsates or is just static. So that's a program. So maybe I should mention what is the Newtonian analog. Would of course be to solve the Laplace equation. And because we are in the region outside of the star, we would have to solve this with a 0 on the right-hand side for a function phi which depends only on r. That's the assumption that we have spherical symmetry, right? And of course we know the solution. So actually we talked about this last Friday for the more general case where we had a cosmological constant. Solution is well known. The Newtonian solution, it's of course phi of r is minus gm over r. And if you like, you could add an integration constant, but that's irrelevant because only the gradient of phi has a physical meaning. So that's the solution. Yeah, this obviously solves this equation. If you look up the Laplace operator in spherical coordinates, you see immediately that this is a solution. And it depends on the mass m. Here is the mass m which enters. And that's the solution in the Newtonian case. So you can do the calculation, even if you have forgotten. If you don't know it by heart, you can do it easily in 5 minutes. Yeah? Solving this problem will take 5 hours. yeah, because we have not only one potential, the phi, now we have 10 potential, the 10 components of the G mu nu, and the equation is nonlinear and in any sense much more complicated than this equation here. So if you really work out the calculation step by step, yeah, I think 5 hours is a realistic calculation. But I do not want to spend 5 hours on this. So I will tell you just the important steps, do the calculations as far as it is possible so that you get the line of argument. But I will not write all the components. I will not calculate explicitly all the components here in the lecture. I will type them up in the lecture notes, but I will calculate only some components by way of example. But the first thing we have to do, if we want to solve this equation, is we have to talk about what is meant by spherical symmetry. Now in our context here where you have a metric. So the first step is to determine the general form of a spherically symmetric metric. Well, in order to approach this program, I suggest to have a look at Minkowski metric in spherical coordinates. Minkowski metric is a space-time of special relativity. So consider, just to begin with, so that we have one spherically symmetric metric to start from, consider Minkowski metric. Whereas the Minkowski metric, I've usually written it in the form, we now use the symbol G as we use for an arbitrary metric. Then we have minus c squared. Well, if I write it in full, then I have the time component, and then the three spatial components, dx, dx, plus dy, dy, plus dz, dz, okay? So that's Minkowski metric. So that's a covector field with another covector field multiplied in the sense of the tensor product gives a tensor field of rank 2, yeah, of rank 0, 2, and that's what the metric is supposed to be. So that's the standard form of the Minkowski metric in inertial coordinates, but we want to consider it in spherical polar coordinates. Okay, that's easy to rewrite this. Spherical polar coordinates are x is r times cosine phi sine theta, y is r sine phi sine theta, and z is r times cosine theta. And from this we can of course easily derive the differentials dx, dy, dz. This is not affected. T remains what it was. So we get dx, and we write this out, cosine phi sine theta dr. So I have differentiated this here. Then minus r sine phi sine theta d phi plus r cosine phi cosine theta d theta. And analogously for dy and dz, dy is sine phi sine theta dr plus r cosine phi sine theta d phi plus r sine phi cosine theta d theta. And the last one is the easiest, cosine theta dr minus r sine theta d phi. And now I can insert these three expressions for dx, dy, and dz here. And what I get is the following. First term is not affected. So if I square each of these terms, in the sense as I take the tensor product with itself, then I get the squares of these three things added together. Here you see I get cosine squared plus sine squared gives a 1, and sine squared plus cosine squared gives also a 1. So there's just dr squared left from these terms. What do I get here? Here I have sine phi and cosine phi gives a 1. And then sine theta comes in all three terms, so I get this squared. So I get sine theta squared d phi squared. And then r was in front of it. So plus r squared sine squared theta d phi squared. And the last one, here I have cosine and sine squared gives a 1. And cosine squared comes with d theta squared. Plus r squared d theta squared. And then, of course, I get cross terms. When I square this, I get these two things multiplied with each other, dr tensor d phi, and terms like that. But you see all of them cancel because they come with plus and minus signs in the appropriate way, so that every term comes twice, once with a plus sign, once with a minus sign, if I have calculated correctly. So that's the answer. That's the Minkowski metric in spherical coordinates. And, well, to link up with standard notation, we may write just dt squared for this here, dr squared for this here. Oh, but I jumped ahead. So here in this line, I should write it in this way, plus r d theta. But now I introduce this shorthand notation. So if I write something like that, a covector field with a square, I mean the covector field multiplied with itself in the sense of the tensor product. So that's a precise mathematical equation. It's a tensor equation. There's nothing like infinitesimally small objects or things like that. It's a precise equation for a tensor field, but you may rewrite it in this form, which is closer to the notation which you find in older books. So there's nothing wrong with using the symbol dt squared or dr squared or something like that. You can interpret it in this way. But what you will also find in old books is that they write, instead of the g, they write ds squared. And this comes, of course, from the idea that you evaluate the metric along a line element. And then you get in Riemannian geometry with a positive metric, you get the length element squared by this expression. But here we have a metric which is not positive definite. So what you write, if you write for the left-hand side ds squared, this is a nonsense notation, because it is not the square of anything. Yeah? Because it can be positive, negative, or 0. So I strictly advise against using this notation, although it is quite common. But it is actually an abuse of notation. So I will actually, the puristic notation is this here with the tensor products, and everything is precise and really mathematically puristic. If you like, you may use this abbreviation. There's nothing dangerous about this. But you should not write ds squared for the left-hand side. Okay, so that was Minkowski metric. And now we ask ourselves, what can I do with this metric? How can I modify the metric without, there's a square missing, right? Here's a square missing. What can I do without destroying the spherical symmetry? So this, of course, I have a t dependence and r dependence, and then the angle expression come only in the combination of this here, which gives the length element on the sphere. And of course, I don't want to destroy this. So I don't want to bring in any angle dependence, which destroys the spherical symmetry. But I can bring in, of course, an arbitrary t and an arbitrary r dependence. So I can multiply each of the terms with a function which depends on r and t. This preserves spherical symmetry, right? And I can also bring in some mixed terms where different covector fields are multiplied with each other. And we have to think about which sort of mixed terms I can bring in. So what is the most general deformation, if you allow me to call it this way, that preserves spherical symmetry? That's a question we ask ourselves. So as I said, we can certainly multiply each term with a function which depends on r and t only. If it would depend on one of the angles, then it would destroy spherical symmetry, right? Because then particular angles would be distinguished from other angles. But I could multiply it with a function, how do I want to call it? Nu. Oops, yes, nu. And it depends on t and r, c squared. And now I use the shorthand notation dt squared. I can multiply this with a function, let's call it lambda, dr squared. I write them in the form e to the power something to make sure that the signature is not destroyed. Yeah, so that the terms have the same sign. So the t lines are still time-like. Yeah? If this is positive, then this means that the t lines are still time-like. So it's possible for an observer to move on the t lines. That's what I want to have. And here I have r squared multiplied with a function, say, mu of t and r. And then comes the angular part, sine squared theta d phi squared plus d theta squared. And now what about the cross terms? If I have a tensor product of dt and d phi, say, or dt and d theta, then again I would get an angle dependence, so I cannot have something like that. But I could have terms dt dr. And as a metric is symmetric, of course, this must come in the form of a symmetrized tensor product. So it must come in this way. Yeah, some people write 2 dr dt for this, where it is understood that the product without the tensor product between the two symbols means the symmetrized tensor product. Yeah, it means precisely this here. So of course here in this term then I can order them as I like, but I will not use this here. And a function here which depends on t and r again. I don't know anything about the sign of this, so I do not write this as the exponential of something. So that's a general form of a spherically symmetric metric, right? It's time dependent. I have a t dependence here. And yeah, it is still spherically symmetric. So there are no directions in space distinguished from other directions. Of course, we are still free to make coordinate transformation. We are free to make transformations of the coordinates t and r. We don't touch the angles. We leave the angles as they are. But we could use the freedom to modify, to change our coordinates r and t. This could help us to make the form of the metric simpler. So for instance, we could introduce a new radius coordinate so that this here becomes just the radius coordinate squared. So we would transform the mu to 0. That would make the expression simpler. So let's do this. Introduce a new radius coordinate. Let's call it r tilde. And it's just introduced in a way that this here becomes the radius coordinate squared. So this is e to the mu of t and r half. So from this, of course, we know how the differentials of dr tilde and the old coordinates are interrelated. We just have to differentiate this. Then we get, let's keep, that's an r. So I first differentiate this here, and then I keep this fixed and differentiate the exponential function. Then it reproduces itself, and it gets and we get 1/2 d mu by dt plus d mu by dr. D mu by dt plus d mu by dr. And now if I want to rewrite everything in my metric in terms of the new coordinate, so if I want to replace my old coordinate r by the new coordinate, then I have to replace the dr here. So this requires to solve this equation for dr. And there's a subtlety. This is glossed over in several books. But actually there are a few subtle examples where it does play a role. So one really has to assume here, it's an additional assumption which is not automatically satisfied, that this equation can be solved for dr. So what we do now is not the most, what we derive now is not the most general form of a spherically symmetric metric. It covers almost all cases, but not all cases. So let's assume. So let's assume this can be solved for dr. So this would give us then an equation. If I solve this, I get an equation of this form. R alpha, no, t has no tilde, r has a tilde. dt plus beta t and r tilde dr tilde. Yeah? Then I get an equation of this form. If I can solve the equation for dr and inserting into G gives an expression of the following form. So wherever I have the dr, I now introduce this expression. So I express the dr as a linear combination of dt and dr tilde. And then I get terms which I have the same structure like this. But everywhere where I had the r, I now have an r tilde. And of course, the coefficients transform. I have new coefficients. So what I get is an expression of the form of this form. I have here a new coefficient, say new or new hat. Yeah, new hat. Of, t and r tilde c squared dt squared plus now a lambda hat dr tilde dr tilde squared. And this term has been transformed to r tilde squared. This was the whole idea, to make this term simpler, plus d theta squared. And then we get the mixed term, which is now something like sigma hat of t and r tilde dt tensor dr tilde plus dr tilde tensor dt. So we have a first slight simplification already reached by making this just the radius coordinate squared. Now we can further simplify this by killing the mixed term. And the trick by which this is done is, well, that's, in English it's known as completing the square. In German we say quadratische Ergänzung. Right? I write this in a way that I get a square, and then I have to subtract the appropriate term so that I still get an equality. So I want to combine these terms under a square. So let's take a c squared out of the bracket. Then I definitely need a new e to the new r tilde half times dt. And from this I have a minus in front, so I need another minus to get a plus. Sigma hat t r tilde. And here I have no c, and here I have a c squared in front, so I think I need a c squared here. dr tilde. So let's see if I square this in the sense of the tensor product with itself. Then I get this term. The mixed term gives this here, right? Where this with this and this with this is multiplied. And then I get an additional term which is not there, so I have to subtract it again. So I have, no, there comes minus, yes. So I need a plus dr tilde squared. This is c to the 4. With this c squared, I get a c squared in the denominator. And this comes with dr tilde squared. And I have another term with dr tilde squared. That's this here. Lambda hat dr squared. Dr tilde squared. And the angular part which is not affected. Okay? Oh, I should have left a gap there, sorry. Let me write this here. Because now we see that indeed we have killed the mixed term. We can call this here, where we cannot call it dt tilde. Because in general, this term will not do us a favor to be the differential of something, right? So this will not be possible to write it in this way. But if we allow for an integrating factor, then it does work. So let's write this e to the nu tilde and the 1/2, right? Yes. So what's inside the bracket? Let's abbreviate this in this way. So we can introduce a new coordinate t tilde with an appropriate integrating factor nu tilde, such that this equation holds. And this, of course, I would call e to the lambda tilde, t of r tilde. And now you see that we have achieved two goals. First of all, this has simplified, this factor has been simplified, and second, the cross term has vanished, right? We have no longer any cross terms. So you can kill the cross terms by an appropriate coordinate transformation. So that will be the form of the metric with which we work now. So that's, oops. Of course, now we drop the tildes. I don't want to have them through the rest of the calculation. So what was t tilde and r tilde in this calculation is now renamed into t and r. And then we get our metric in the form following much nicer form than we had before. Minus c squared e to the 1/2 is squared away. So I get, if I drop the tildes, nu of t and r dt squared e to the lambda t and r dr squared plus the angular part d phi squared plus d theta squared. So as I said, there are quite a few books which tell you that this is a general form of a spherically symmetric metric. That's not quite correct, because we had to assume that we can solve this equation for dr. And there are examples where this is not satisfied. Just to give you an example, if you have ever heard about wormholes. Yeah, a wormhole is something where the r coordinate begins at -infinity, goes through a minimum, and then goes out to plus infinity again. And this thing in the middle, that's called the throat of the wormhole. And near the throat, this condition is violated. So I cannot solve this equation for dr near the throat. So the wormhole metric cannot be brought in this form. But at the moment, we are not talking about wormholes, we are talking about Schwarzschild. And for Schwarzschild, everything is fine. So this is, if we deal with Schwarzschild, this is really no restriction of generality to assume that the metric is of this form. And what are the range of the coordinates? So that's a form of the metric with which we will go into the field equation. Yeah? So this was the first preliminary step. We have brought the metric in a convenient form for the following calculation with the help of coordinate transformations. And now with this metric, we now go into the field equation, and we really have to solve the field equation, which become, of course, differential equations for nu and lambda, right? So it will give us a coupled system of differential equations for nu and lambda, which we will have to solve. But before doing this, I should make quite clear what the range of the coordinates is. Well, that's more or less self-explanatory. The range of the coordinates is what? Our time coordinate, of course, should run from -infinity to plus infinity. Yeah? We want to have the space-time for all times. The r coordinate is bounded by the radius of the star. And as I said, I want to allow for the situation that it depends on time. And it goes out to infinity. And the angular coordinates, of course, have their usual range. So theta goes from 0 to pi, and phi goes from 0 to 2 pi, right? So that's that's the form of the metric with which we will work. So the coordinates are t, r, theta, and phi, and that's their range. So now, what do we have to do? This is the metric. So this is g mu nu dx mu dx nu. Yeah, so from this expression, we can read the g mu nu's. So we read that gtt is this here, grr is this here, g phi phi is this here, and so on. Yeah? With the g mu nu's known, we can calculate the gammas. Remember, the gammas are given as first order, in terms of first order derivatives of the metric. If we have calculated the gammas, we can calculate the components of the Ricci tensor. And then we can equate them to 0. That's what we have to do now. And as I said, that if you really do it line by line, it takes a lot of time. So I will not do the calculation in full here on the board. I will calculate for you one set of Christoffel symbols, but not all of them. And I will calculate for you one component of the Ricci tensor. And for the other ones, I will just write the results to the blackboard. But I will type it out in the lecture notes. So the first step, or actually this was the first step, so now comes the second step. So now we have to calculate the Christoffel symbols. And whenever you have to calculate Christoffel symbols for a pseudo-Riemannian metric, not for an arbitrary connection, for a connection which comes from a metric, then it's always a good idea to do it with the help of the geodesic equation. So of course what you could do is, you could use the formula which gives you the gammas in terms of derivatives. So we could use, but we will not, we could use this expression. Remember how gamma mu nu sigma was given in terms of the metric? So it was this expression with 3 derivatives here, dg minus dg. Here's the summation index rho. It is here, it is here, it is here. And then I copy the indices from the left-hand side. Nu sigma, nu sigma, nu sigma. So with the g mu nu known, yeah, they can be read from this expression. We can calculate this. We can invert the matrix of the g mu nu. Well, in this case, it's fairly simple because it's a diagonal matrix. Yeah? It has only diagonal entries, so it's fairly easy to calculate the inverse. But nonetheless, you have to calculate the sums, and so it's a little bit awkward to do it with this formula. You could do it, but there's a more clever way. And the more clever way is to use the geodesic equation. So instead, we will use the Lagrange function for the geodesic equation. Well, what was it in general? L of x and x dot was 1/2 g mu nu, which depend on x mu dot, x nu dot. And in our case, we can read what the coefficients are. So in our case, we get 1/2 minus c squared e to the nu t dot squared. The dot, I'll write it in a minute. The dot means derivative with respect to the curve parameter. Yeah? Which you could choose any symbol for the curve parameter, but please do not use t, because t is already the time coordinate. Yeah? So then you get really confused. So I usually call the parameter of a geodesic S if I don't want to specify the causal character. If it is a time-like geodesic, then we could write tau. Then we could use proper time, right? But the geodesic could also be light-like or space-like. Then it doesn't make sense to call it tau. So in general, I write S. And the dot means derivative with respect to S. So that's why here t dot occurs, which would look very confusing if you would call the parameter t. So that was the first term. Then comes e to the lambda r dot squared plus r squared sine squared theta phi dot squared plus theta dot squared. And this bracket is closed. So what do we do now? This Lagrangian gives us a geodesic equation. So if we write the Euler-Lagrange equations with this L, then we get the geodesic equations. And in the geodesic equations, also the gammas enter. And it's much more convenient than using this equation to write the Euler-Lagrange equation and to read the gammas from this. So use the Lagrangian, write Euler-Lagrange equations. So just to remind you, that's how they looked like. Minus dl by dx is 0. And of course, we have to do this for all 4 coordinates. This is a geodesic equation. So what we get here must be equivalent with the equation x mu double dot plus gamma mu nu sigma x nu dot x sigma dot is 0. So we write this for the 4 components, compare it with this expression, and read the gammas from this comparison. So that's usually the quickest way to determine the gammas. I will do this for x mu equal t. And for the other 3 components, I will just write the result. So what do we have to calculate? D by ds. Now x mu is now t. So I have to differentiate L with respect to t dot. So then I get the 2 kills the 1/2. So I get minus c squared e to the nu t dot. Right? This is this here. And then minus dl by dt. X mu is t now. Do you see a t? No. Yes, of course you see a t here in the u and in the lambda. So this is minus 1/2 minus c squared e to the nu d nu by dt t dot squared plus e to the lambda d lambda by dt r dot squared. And the whole thing is 0. So now we have to arrange the terms in a way that we can compare with this expression. So we want to solve for t double dot. Yeah? That's essentially the goal. Well, that's not too difficult because this comes here in a very natural way. So we get minus c squared e nu t double dot minus c squared e nu d nu by dt t dot plus d nu by dr r dot. And then I have this t dot. So that's the first term, right? Did I forget something? No, I think so first I left this constant and differentiated the t dot, then I get a t double dot. And then I let the t dot constant and differentiate this with respect to the curve parameter s. I do this with the chain rule, right? d nu by dt t dot, d nu by dr r dot. Okay, and here, yeah, I just write the terms a little bit more conveniently. d nu by dt t dot squared minus 1/2 e to the lambda d lambda d2 r dot squared, and that's 0. So I want to solve for t double dot. So I take this to the right-hand side and multiply everything with c squared e nu. So I get here minus this bracket, d nu by dt t dot squared, minus d nu by r dot t dot. I multiply with 1 over c squared e to the nu, then this is killed. I get plus 1/2 nu t dot squared. And here I get what? Here I get minus 1/2 divided by c squared e to the lambda minus nu. Yeah, because I divide everything by e to the nu. D lambda dt r dot squared. And this must be, if I compare with this equation, this must be gamma, now minus gamma t u sigma x nu punkt, x nu dot, x sigma dot. And you see, here you can read now the gammas with an upper index t. And I will do this now. And then we have done 1/4 of the task. And the other 3/4 I will not do on the board. What I have to use is, of course, the symmetry of the gammas. Remember, we are dealing with a torsion-free connection. The Levi-Civita connection is torsion-free, so the gammas are symmetric in the lower indices. Otherwise, this method wouldn't work, because we only get terms where the symmetrized gammas enter, right? So you cannot use this method in series with torsion, at least not so easily. Okay, so what can we read from this expression? Oh, I think I can combine two terms, right? I have here the same term, once with 1/2 and then with minus 1/2. So allow me to do it in this way. Yeah? So I get it with a minus 1/2. So this would be gamma t, right? That's this term here, where here I have x nu and x sigma both equal to t. So this is, I have a minus sign here and a minus sign here, so it is plus 1/2 d nu by dt. And this here gives me the gamma t tr, which is the same as gamma t rt. And this is because I have to symmetrize this. Yeah? I have to write this as 1/2 times the term with r dot t dot plus t dot r dot. So with one index combination, I get this with a factor 1/2. This is 1/2 d nu by dr. And the last one is gamma t rr, that's this here. I have a minus sign on both sides, so I get 1 plus 1 over 2c squared e to the lambda minus nu times d lambda by dt. And these are the gammas with an upper index t. Let me check if I got it right. Where are the gammas? Here they are. 1/2 d nu by dr, 1/2 d nu by dt, 1 over 2c squared e to the lambda minus nu d lambda by dt. Yes, excellent. And we do it analogously for the other components. And I just write the results. So I get the gammas with an upper index r by calculating the r component of the Euler-Lagrange equation. So here I have an gamma r is 1/2 d lambda by dr. Then I get gamma r t TR, which is the same as gamma R RT. This is 1/2 d lambda by dt. And the gamma RTT, which is c squared half, e to the nu minus lambda d nu by the r. So these are the Christoffel symbols with an upper index r. The other ones, oh no, there are two more. So gamma r theta theta is also different from 0. That's minus r e to the minus lambda sine squared theta. No, sorry, this was gamma r phi phi. Now comes gamma r theta theta. That's minus r e to the minus lambda. And the other ones are simpler. So the ones with an upper index theta are this here, gamma theta r theta, which is the same as gamma theta theta r. It's just 1 over r. Gamma theta phi phi is minus sine theta cosine theta. And the ones with an upper index phi, gamma phi theta phi equal gamma phi phi theta is cotangent of theta. And the last one is gamma phi r phi, which is the same as gamma phi phi r is 1 over r. So these are the non-zero Christoffel symbols. So all Christoffel symbols I have not written are 0. And now I should be very careful not to erase this, because I need this for calculating the Ricci tensor. Okay, these are the gammas. Now comes the Ricci tensor. Remember how the Ricci tensor is, well, first of all, the curvature tensor can be expressed in terms of the gammas. This was this fairly ugly expression with 4 terms. And well, fortunately, we don't need the curvature tensor. This would be even more work to calculate this. We only need the Ricci tensor, which is a contraction. So this is considerably simpler. So now calculate the Ricci tensor. And again, I will do it only for one component on the board, and for the other ones, I write the result. So the Ricci tensor had 2 indices, r mu nu, and it was given as a contraction of the curvature tensor over the first 2 indices. That's my convention. Yeah, that's a good occasion to repeat that other authors use other conventions. You have to really be careful if you look this up, if you compare results from different books, that the Ricci tensor is not defined uniquely. Well, if you set it equal to 0, there's no problem with the sign. But if you deal with a field equation where this is not 0, then the sign really matters. Okay, so this was my convention that I contract over the first pair of indices. And then we can use this formula, which gives me the curvature tensor from the gammas. So I have the index pair rho here, and the remaining ones are on the gamma. And then in order to produce a second term, I have to recall that this is antisymmetric in the first 2 indices. So the second term with a minus sign should result just by interchanging these 2 indices. So I have the rho again here, I have the nu again here, but this rho and this mu interchanged. And here I do it in the same way. I write the rho here, sigma here, mu nu on the first gamma. And then I interchange rho and mu, the lower indices rho and mu. So rho and sigma and u remain where they were. This becomes a mu, this becomes a rho. That's what we have to calculate. Yeah, and that's, well, it's not exactly great fun to do this calculation, but one has to do this. Of course, there are computer programs which do this for you, yeah? But I think once in one's life, one should have done it by hand to get a feeling for the structure, yeah? So there are computer programs that feed the metric in, and they give you the Christoffels, the curvature tensor, the Ricci tensor, whatever you like, yeah? But then, of course, there's always the danger of making typing mistakes, yeah? And I think the opportunity to make typing mistakes is almost as big as the opportunity of making calculational mistakes. So you shouldn't trust the output, what you get from a computer calculation. So I will do it by hand for one component. So I will do it for RTR, which is the same as RRT. The thing is symmetric, yeah? The Ricci tensor for a connection which comes from a metric is symmetric. In general, the Ricci tensor of an arbitrary connection is not symmetric. But if it comes from a metric, if it is a Levi-Civita connection of a metric, then it is symmetric. You can read it from this expression. Yeah, so with the symmetry of the gammas, it's easy to check that this is symmetric in mu and u. So the first index is r, the second is t. So what do I have to calculate? I have to calculate this here for rt. Minus d, gamma, rho, rho. And now this is wait a minute. The mu is r, rt, plus gamma sigma rt, gamma rho, rho sigma, minus gamma sigma rho, gamma rho sigma, and mu was r, and nu was t. So that's what you have to calculate. And for this, of course, we need the gammas. So these are four terms, right? There's a summation over rho. So we have to look for which upper indices do we get a Christoffel symbol with lower indices r and t. We get it for an upper index t and for an upper index r, and I think for nothing else. So we have the first term where rho is t, and then the second term where rho is r. So that's this here. The other terms give 0. Yeah, because this here for rho equal theta and for rho equal phi is 0. It's not there. Then we have this term here, minus dr. So here we have Christoffel symbols where the one lower index is a t and the other two indices are the same. So this gives something for rho equal t. I don't want to write them underneath each other. I get something where both are r, right? Gamma r rt, that's non-zero. And the other ones, here I don't have a lower index t, so that's already everything. That's the second term. Now comes this term. So I have lower indices RT. Then the sigma could be, for instance, t. So I would get here t. And these two indices must be equal. This is possible for t and r. So that's the term where sigma is t. So I have a term where sigma is r. So then this lower index is an r. And here I have all four terms. All four terms are non-zero. T, R, R, theta, R, plus gamma, phi, R. So that's this term. And now comes the last one. Minus gamma. So I have a t here. What combinations can I get here? For instance, where both are t. Then I have here gamma r tt. And where both are r. And I have here gamma r rr. And where one is r and the other is t, and vice versa. Minus gamma t tr, gamma r rt, minus gamma t rt, gamma r t r. That's it. Fortunately, a few of them should drop out. Let me see. The R. This here drops out against this here, right? Where do I have a TTT? I have a TTT here. And this also goes away. RRT, RRT, TRT. That's these two. Anything more? Maybe this here? RR, yes, this also. And I think that's it. The rest we have to calculate. So I continue up there. So where was the equality sign? Here. So that's the first term. dt of gamma TRT. TRT is this here. 1/2 d nu by dr. And the second term is this here. Minus dr gamma TTT. Gamma TTT is this here. 1/2 d nu by dt. They are cancelled. This here plus gamma RRT, RRT, 1/2 d lambda by dt times gamma TTR, TTR 1/2 d nu by dr. I could make a bracket here and add these two terms. Theta theta r is 1 over r, and phi phi r is also 1 over r. So I get 2 times 1 over r. This was this term here. And the last one is this here, minus gamma RTT, gamma RTT. That's this long one. Minus RTT c squared half e to the nu minus lambda d nu by dr. Times gamma TRR. Gamma TRR. 1 over 2 c squared e to the lambda minus nu d lambda by dt. Okay, now everything becomes fairly simple, hopefully, if I didn't make a mistake. So you see, these are the same terms, right? Partial derivatives commute. Here I first have the derivative with respect to r, then with respect to t. Here it's the other way around, but they commute. So these two terms cancel. And this term should cancel against this here. You see the two exponentials kill each other. The c squares kill each other. Then I get 1 over 4 d nu by dr d lambda by dt. And here I get the same term with a plus. So this cancels this here. And I get a comparatively mild result, 1 over r d lambda by dt. That's it. Yeah? So that's the TR component. And in this way, now you have to calculate all the other components. How many are there? How many components has a Ritchie tensor? 10, yes. So these are, each index takes 4 values, so this would give 16, right? But it's symmetric. So the upper right-hand triangle is the same as the lower left-hand triangle. So you have the diagonal and this triangle. The diagonal is 4 and the triangle is 6. 4 plus 6 is 10. So we have calculated 1. So now we would have to calculate the other 9, yeah, which give expressions of the same kind. So I abstain from doing this on the board. I just give you the result. So I begin with the mixed terms, where I have different indices here. So we have calculated the first of the mixed terms already. So the other ones I just write down. So we have r theta t, which is the same as rt theta, is 0. I shouldn't be too generous with the space, so let me put this here. R phi t, which is the same as rt phi, is also 0. And r theta phi, which is the same as r phi theta, is also 0. So the complicated things are the diagonal terms. So the diagonal terms are following. RTT is fairly long. RTT is c squared e to the nu minus lambda, 1/2 d2 nu dr squared, plus 1/4 d nu by dr squared, minus 1/4 d lambda by dr, d nu by dr, plus 1/r d nu by dr. That's not the whole story. Now come time derivatives, minus 1/2 d2 lambda dt squared, plus 1/4 d nu by dt, d lambda by dt, minus 1/4 d lambda by dt squared. That's RTT. RRR is also a bit awkward. Where is it here? It's minus 1/2 d2 nu dt squared. Sorry, dr squared. Minus 1/4 d nu by dr squared, plus 1/4 d lambda by dr, d nu by dr, plus 1/r d lambda by dr, plus 1/c squared e to the lambda minus nu, 1/2 d2 lambda dt squared, 1/4 d lambda by dt squared, minus 1/4 d nu by dt, d lambda by dt. So these are the two unpleasant terms. The remaining two are nicer. R theta theta is 1 minus e to the minus lambda minus r ½ e to the minus lambda d nu by dr minus d lambda by dr, and r phi phi is just sine squared theta times r theta theta. So these are the components of the Ricci tensor. So now we can write down our field equations, really as differential equations for lambda and u, right? All these expressions are given in terms of derivatives of lambda and u. So if we set all components of the Ricci tensor now equal to 0, that's our field equation, we get a second order differential equation for lambda and nu. And how many equations do we get? Well, RT, that was the one I've calculated. This gives the condition that this is 0. Then we get one, if we equate this to 0, we get a third one from this here. And we get only one from these two, because they just differ by a factor, which is, of course, not identically 0. So we get only a fourth one. So we had 4 conditions. These conditions, of course, are automatically satisfied if the field equations hold. So the field equation gives 4, or let's say a system of 4, of course coupled, nonlinear, second order partial differential equations for u of R and T and lambda of R and T. And we have to write them down and then to solve them. I should leave the metric on the board. This would be helpful. Oops. So I get 4 equations. I call them S1 to S4 so that I can quote them later. So the first one comes from the equation that RTR is equal to 0. RTR is there in the first and second line. So 1 over R, of course, is not identically 0. So this just tells us d lambda by dt must be 0. So lambda cannot depend on time. Yeah? Lambda is a function of R only. And of course, we can use this. When we now write S2, S3, and S4, we can already use this fact. So we can omit all terms which involve time derivatives of lambda. This makes it considerably shorter. So the next component would be RTT. I've written as the second one, yes. So this is RTT equals 0. So you see, there are a lot of time derivatives of lambda. So we can forget about them, yeah, because they are 0. So we have only set this here equal to 0. It's of course non-zero. So just this round bracket here must be 0. And I think I can multiply it with 2, then it looks nicer. So then I get second derivative of nu with respect to R. Plus 1/2 d nu by dr squared minus 1/2 d lambda by dr lambda by dr d nu by dr. And the last term is 1 over r d nu by dr. The third equation is r equals 0. At this line. And again, we have a lot of terms which involve time derivatives of lambda. So they are 0. So we have only the first 4 terms. And I think I multiply with minus 2. And I get d2 nu dr squared plus 1/2 d nu by dr squared minus 1/2 d lambda by dr d nu by dr, and then minus 2 over r d lambda by dr. 2 over r? Oops. I forgot here a 2. I forgot a 2 here. I had multiply everything with 2. So I get here also a 2. Yes. Should be the same factor in both equations. So I hope now all the factors are correct. I will check the equations in a minute with my notes, because if they are wrong, we will never get the Schwarzschild metric. So the last one, this is r theta theta equals 0. And this is simply this expression as it is there on the board. 1 minus e to the minus lambda minus r half e to the minus lambda d nu by dr minus d lambda by dr is 0. Let me check if I got everything right. Lambda by dt, yes. r squared plus 1 half minus 1 half plus 2 over r. It's 1 half minus, yes. Yes. Okay, that's fine. So that's what we have to solve now. Well, S2 and S3 look very similar, right? So I think it's an obvious idea to subtract one from the other. Then we get just that sum of these two terms must be equal. So we get d mu by dr. I subtract the equation, so I get this with a plus sign. And this is 0. So I can differentiate this with respect to t. Yeah, that's a good idea. I get what? I get the mixed derivative of nu. But if I write this on the other side, this is minus the second derivative of lambda. But lambda is independent of t. So with S1, this is 0, right? So the mixed derivative of nu is 0. This means nu must be a sum of a function which depends only on t and another function which depends only on r. Yeah? So from this we get that nu, which is a function of t and r, is a function of t alone plus a function, how do I call it, nu tilde, of r alone. Yeah? That's a general solution to this partial differential equation, that this here is 0. Yeah, if you differentiate this twice, you get first the derivative of this here, which depends only on t, and if you differentiate it again, then you get a 0. Yeah? And the other way around also, for the other term also. So that's indeed the general solution. And with the help of this, we can now, let's give a name to this equation here. Let's call this, I don't know, how shall we call this, star? With star. We get, well, if I differentiate this with respect to r, I get d by dr nu tilde of r plus d lambda of r, which depends only on r. So I can again write a total derivative, and this is 0. And that, of course, is very easy to integrate, right? So that's, of course, nu tilde r plus lambda of r is a constant k. So we have brought this coefficient here, this coefficient. This was e to the nu, which depends in the beginning of on t and r. This was the term which came with dt squared in the metric. Yeah? We have now brought this to a considerably simpler form. We have written it at e to the f of t times e to the nu tilde of r dt squared. And the nu tilde of r is this here. So this is e to the f of t, e to the k, e to the minus lambda of r dt squared. Or if I continue, here I have a t, so I write this next to the dt squared. That will be convenient. To the ft dt squared, because now I have something which involves only t. So I can make this into a new time coordinate. I just transformed the time coordinate, so I call this dt squared, tilde squared, or let's call it d hat squared, because we had already a dt tilde. And I have now a new time coordinate. I think I include the k also. Do I? Yes, I include the k also. Oops. So let me write this here, minus lambda of r, and e to the k, and this is here. Yeah, if I have a function here which depends on t and r, then of course this doesn't work, right? This would not be a transformation just of one time coordinate into another. But as this depends only on t and not on r, I can make it into a new time coordinate. I just transform the time coordinate, leave everything else as it was, and then my metric becomes a simpler form. So what was e to the nu of t of r in the general form has now become e to the minus lambda of r, which is the same lambda as for the other term. So, and now we have, without realizing it, we have proven the Birkhoff theorem, the theorem that a spherically symmetric metric is time independent. Because as you see now, the time dependence has vanished from all coefficients. I think now I can erase this. Can I? Yes, I think so. And then we are almost done. The rest is just solving an elementary ordinary differential equation for lambda. To think of Schwarzschild did all this when he was at the front in World War I. So I now drop the hat. So what is t hat here is again called t. And then we write the metric in the convenient form, which we will use in the following. So dropping the hat, the metric reads what? So there's a metric, G is minus c squared. E to the nu of t and r has now become e to the minus lambda, which depends only on r. Then comes a d hat squared, but I just write dt squared, plus e to the lambda, and lambda depends on r only, dr squared. And the angular part, we haven't done anything to the angular part during the whole calculation. D phi squared plus d theta squared. So what has become of our system S1 to S4? It's been reduced to what? So S1 was an equation that lambda is independent of t. Well, with this form, this is already used. So there's no further information from S1. What about S2? So the nu has now become minus lambda. Yeah, where we had the nu before, we now have a minus lambda. So I replace nu by minus lambda. So I get minus, and that's a total derivative now, because everything depends on r only. R squared plus 1/2 d lambda by dr squared. And the same term comes another time, so I just erase the 1/2 minus 2 over r d lambda by dr. Well, S3 is the same equation where we had in S2 as a term nu, we have in S3 minus lambda, but the two things are the same. So S3 gives no further information. It's automatically satisfied. And S4 gives something. S4 gives 1 minus e to the minus lambda, which is a function of r only, minus 1/2 e to the minus lambda. And nu is minus lambda, so I get minus 2 d lambda by dr. So that's the system we have to solve. But before solving this system, I think I will not do this today, I will do this tomorrow. But then we have the Schwarzschild metric, I think, in 15 minutes or so on the board. Before solving this, I want to emphasize the fact that now we have reduced the metric to a time-independent form. Now, the metric coefficients G mu nu, are time independent. Yeah, we started with a spherically symmetric metric which was allowed to depend on time. Then we have inserted this into the field equation, and we have found out that after an appropriate coordinate transformation, we can transform the metric to a time-independent form. If we choose the time coordinate appropriately, then the metric is time-independent. And that's what is called the Birkhoff theorem. We have thus proven the Birkhoff theorem. So by that one means the following theorem. And this was proven not by Schwarzschild. Schwarzschild didn't know this. It was proven by George Birkhoff in 1923. So this was 7 years after Schwarzschild. Actually, I read in one source that there should be an earlier proof of this by a gentleman by the name of Jepsen. I've never heard about him. So apparently, I think he's Norwegian or Swedish or something like that, Scandinavian in any case. So maybe Birkhoff was not the first who proved this, but he's usually credited for this. And he definitely very clearly stated this in 1923. And the theorem is any spherically symmetric solution to Einstein's vacuum field equation and here I mean the field equation without cosmological constant. The equation R mu nu is equal 0 is time independent. And that's a remarkable result as to the physics which is contained in this statement. It means that even if a spherically symmetric body is oscillating, Yeah? The gravitational field outside is time independent. So one could phrase this in the way that one says there are no spherically symmetric gravitational waves. Yeah? That's what it says. You could assume that if a star pulsates, that then it would emit gravitational waves, where the wave surfaces are just spheres. That's imaginable, yeah? You could think of something like this. But they don't exist. Just mathematics prohibit them. If I have vacuum around the star, then such waves do not exist. The field is perfectly time independent, it is static. So, of course, the analog of the Birkhoff theorem also holds in Newton theory. Yeah? Also in Newton theory, if you have a pulsating star, the gravitational field outside is static. It's always a 1/r potential. If you are away from the body, if you measure the gravitational field, you do not see if the body is oscillating or not. You only see the total mass, nothing else. Yeah? Of course, if the spherical symmetry is violated, then of course you see something. But as long as it moves just in a spherically symmetric way, you don't see anything. And that's the same in general relativity. So gravitational waves cannot be spherically symmetric. Yeah. So what we have to do is we have to solve this system of equation now for one single function lambda of one single variable. And this can be done in elementary fashion. So I think I will do this in 15 minutes or so. And then we have the Schwarzschild solution on the board. And then we can discuss it, which we will do at length. So we will see what observable effects in the solar system actually are predicted by this solution. And we will discuss in which way this solution predicts the existence of black holes, spherically symmetric black holes. So they will come out of this calculation. So that's the program for tomorrow. See you then.